Okay, hi everybody. My name is Greg Freeman. My day job, I work for Applied Materials. I work in robotics and mechatronics for semiconductor tools. So we make the machines that make semiconductors. So a lot of these machines run at atmosphere, and that's environment where you can't have people. And there's also a lot of delicate processes to lay out all the layers of a semiconductor machine. So we've got lots of robotics and mechatronics that do different steps in the process. And I use Python and C++ to create algorithms and software. One thing I don't use in my day job is ROS, but I'm really excited about ROS, with ROS being open source robotics. So it's kind of a side project where I wanted to learn ROS and also play with toy robots with my kids. There's this little robot that I built with my kids, and I'll talk a little bit more about that later in the talk. Okay, overview, ROS equals operating system. It's a framework, a set of tools, packages in Python and C++ for robotic applications. And it's got state-of-the-art algorithms. So there's been a whole lot of university research throughout the years that's been building up to a lot of this capability. We're going to talk about the ROS ecosystem, some important concepts in ROS, how to get started, and talk about some of the major packages in ROS. Here's some neat videos to kind of get you excited about what ROS can do. There's a whole lot of startups that are using ROS and a lot of big companies that are using ROS as well. I'm showing two of the high level of ROS packages. So Move It and Nav are kind of two of the big high level ROS packages. So Move It, the idea is they're robots that have movable linkages. So it has to do all the path planning of all the different linkages in the robot. Nav2 is navigation. So this is for mobile robots. So they've got to navigate with different sensors and build a map. There's something called SLAM. We'll get into that a little bit more later. So there's lots of really cool things that you can do with ROS, and that's what got me excited about learning this and sharing with you guys about what I learned. So we've got a lot of these different stuff. Let's see. Moving on. Okay, so fundamentally, there's a ROS core. So those other ones were at the high level, the big packages of high level, but now we want to go down to the low level. Fundamentally, what's so ROS core is this kind of low level. So the idea is you've got nodes that can communicate. And so ROS packages are software that are built on the ROS core. And so we've got either ROS Pi, which is the Python core, or ROS C++, which is the C++. And so they communicate with this publish subscribe messages, and they're organized by topics. And so I've got some little diagrams here. So we've got a node, it's got subscription topics that are inputs, and it's got publish topics that are outputs. The kind of hello world of ROS is this talker listener, where the talker is publishing a topic and the listener is subscribing to that topic. There's a little more diagram to the right. We can have a topic go to multiple nodes, and we can also have special types of things like services, which are a little bit like RPC, where you've got a request and a response, and you can have the appropriate messages going back and forth for that. Robots. So fundamentally, how are robots different from other software? And I just wrote this simple diagram. So our controllers are kind of main software, and the controller will sense the world. So there'll be different sensors. Maybe it's cameras, maybe it's push button sensors, maybe it's infrared sensors, laser scans, lots of different ways to sense motor encoders, temperature, all kinds of stuff. So you've got sensors that go into your controller, and then your controller outputs commands to an actuator, and that actuator changes something in the world, and then the world responds and then feeds back to your sensors. So so the idea is you've kind of got this this control loop where you're acting on the world and then sensing the world and making changes to what's in the world. Simulation robots. So because ROS has got all these nodes that can communicate with each other, we can replace the real sensors, actuators in the world with simulated sensors, actuators, and world, and use the exact same software. And simulation is really important because the realistic simulation enables reinforcement learning and also good software. We'll talk a little bit more about that later. But the idea is we've got all these nodes communicating. So your controller can be composed of many different pieces of software that are all communicating. But at some point, they have to sense the world and control some actuator. And we can replace these components with simulation components. And then we can simulate a robotic system and have it learn about things in its simulated world. So why do we call ROS an operating system? It was originally released for Linux only, and so kind of going back to that history, it kind of started with an operating system. It's got packages with lots of dependencies, so lots of entanglement, so not as easily portable. Now we've got ROS that's installable on both Windows and Mac OS. Not everything works when you do those other environments, so Linux is still kind of where you need to run it to have all the functionality. But there's still a lot of things you can do in Windows and Mac. In development, I think this is kind of cool, but there's not a lot of momentum, is this thing called RoboStack. So this is essentially a way to install ROS on the Conda. We've got lots of packaging package dependencies, so it's kind of neat, but um, it's a little bit on the development side. Okay, history. ROS first started in 2007. It was originally a lot of university robot research. So back then, robotics was kind of just in the university labs, and they established a open source robotics foundation to work on. There's been some companies throughout the years that have sponsored it. The Willow Garage was one of the ones in the past. In 2012, there was a group to do ROS Industrial. So the idea was kind of take it out of the university and make it more applicable to the business environment, where you've got some of these different commercial control systems with PLCs and whatnot. Um, 2005, they introduced ROS2, and I'll be talking about the differences between ROS1 and ROS2. It's a community, so just like we've got Python enhancement proposals, they've got ROS enhancement proposals. And so as they're maturing ROS, they've got this structure in place to handle those open source issues. And so in 2021, we've got a whole lot of software startups using ROS, and also some big companies too. So there's a lot of really fascinating stuff that people are doing with ROS. There's a whole lot of versions of ROS, and as I've been learning ROS, I found the version is really important. And they've got really cute names for the versions. So we've got Rolling Ridley. So this is kind of like the latest, the nightly build type of version. And then we've got these kind of names that start with a letter that proceed through the alphabet. So if we look at ROS1, we've got melodic and we've got noetic. So noetic is the latest ROS1 version. In ROS2, we've got Foxy and we've got Galactic. And there's also another one that starts with H that's coming. So I recommend Foxy. I found Foxy works with a lot of the packages. So and also there's more long-term support for Foxy. So they're going to be no longer supporting Galactic and kind of jumping. So there's some interesting pieces here. One of the really important things for understanding the version is that there's a whole lot of examples out there in ROS, and I found that not all of them work. So if you look at an old example in ROS and try to run it, it's not going to work with the latest code. So it's important to kind of think about the release when you see some information on some neat demos. Challenging opportunities for develop. One of my old bosses said, it's not a challenge, it's an opportunity. And so so a lot of, you can switch any challenge into an opportunity. And so there's kind of a different packaging philosophy in ROS than we're used to in Python. And also virtual environments have limited support. You can do a virtual environment, but you can't use a Conda environment, for example. I mentioned the package versions are important. So those releases, those releases have a binary releases, so it's a important. So that kind of gives a point where a lot of the packages work together within a particular binary release. And so there's a lot of breaking changes when they release new versions. But this is also an opportunity for, as an open source developer, there's lots of opportunities for making improvements. So if you see a demo that doesn't work, you can say, why does that not work? And you can change it. So it's I was looking at a tutorial, and it turned out to be not a tutorial on how to use ROS, but how to fix ROS tutorials. And I was like, oh, that's actually kind of useful. Okay, ROS 1 versus ROS 2. So there's some people still using ROS. So this is to think like a couple years back where we're talking about Python 2 versus Python 3. Not everything was supported in Python 3, so still people were using Python 3, kind of roll back in history a number of years. So there's some people with legacy code bases still running ROS 1, but any new project, ROS 2 definitely. Different version of C++. Python 2 originally, but everything's Python 3 these days. The launch files used to be in XML. Now they're in Python. The old build system used to be Catkin. Now it's ColdCon. There's real-time support in ROS 2. For the messaging, ROS 1 had a master that controlled all the messaging and the discovery, where there's a distributed messaging system in ROS 2. And I kind of compare some of these two because, as you see, different examples and tutorials that people have put out through the years. Some of these are kind of clues to know, hey, is this an old version of ROS that they were using, or a new version of ROS? And so kind of navigating all this kind of wealth of information is a little bit tricky, but stick with ROS 2 because that's the newer one. Special types of nodes. So a node is the most general type of ROS package. And so the idea is you're kind of publishing information, you're subscribing. A service is an alternate type. So it's like an RPC where you can do a request and then get back information from another node. There's also an action. So in robotics, many times you're trying to achieve some type of goal. You're having a control system, and you've got some desired place that you want to be, and you're closing that loop to get to some goal. And so they've got a special type that's a goal. So you can say, here, I want you to navigate to this point. And then there can be a controller that helps you achieve that goal and makes them intermediate steps to get to that goal. And then once it reaches that goal, or maybe you can retask it with a different goal. We've also got executors. So the idea is we've got all these nodes, which are modules of software that talk together. If you scale this up, you've got lots of nodes that are sending messages. And the bigger this gets, this becomes slow. So the idea of executors is that you can put a collection of nodes together within the same process and use intra-process communication to make things faster. Okay, common tools, we've got ROS 2, which is command line. So there's a lot of things you can do with command lines. You've got parameters to configure nodes. We've got the launch files. So launch files basically is a setting. So you can say, here, I want to start the world with all these different nodes together. Where the command line, you can say, ooh, I want you to start one node. The launch file says, here, set everything I need to do this particular robot application. We've got URDFs. These are universal robot description files. And so this is basically telling the system what's the geometry of your robot, what are the linkages of your robot. We've got bags for playback and recording, and the build system. ColdCon is the build system. And then we've also got DDS, which is a way of passing the messages. And so there's a lot of these things can be kind of mixed and matched with different things as things get more advanced. But ROS comes with kind of the basics to make things happen. So what's ColdCon? It's this build system. So it's tools that are built on top of CMake for the ROS ecosystem. So it's kind of like CMake on steroids. And so just like the Python ecosystem, where we've got lots and lots of dependencies, in ROS, we've got the combination of Python and C++. And this ColdCon build system helps us kind of build a lot of these packages so they can work together and discover other packages. We kind of have environments in Python, but the idea in ROS is they kind of layer environments. You could say, I want to take the base installation of Foxy, and then you could say, I want to also layer on top of some packages that I've import from third parties, And then you could also layer on top of that environment where you're building your own code. So I do kind of add environments together. Um, and then you can kind of source these different, there's a setup bash script that's for each layer in your environment that you need to source. And then it basically adds the queues into your environment to know what packages are available to your ROS installation. There's this robot stack, which also has there's a Vinca template generation system that generates Conda recipes for ROS packages. I think this is cool. There's not a lot of momentum in the ROS community, but I thought this was really neat that they were using Conda to build ROS. And so the idea is you can, instead of having the installation process that you go through with ROS, it's just Conda installable to get the packages. And Conda is good to handle C++ and Python dependencies. So kind of a neat match there, but but a lot of the ROS community is used to this layered environments where you source your environment and go through this installation process. Okay, moving on. We've a lot of things are done through the terminal. We've got Gazebo, and this is for kind of simulating your real world environments. You've got physics, graphics sensors. We've got RViz, which is for 3D visualization and you've got tools for robot and motion planning. There's RQT, which is for plotting data and viewing logs, and each of these have plugins. And with the open source community, there's a lot of people that have extended these tools to do lots of different applications. Packages. Okay, we talked at the beginning. So Move It. It's the way for robots with linkages and path planning of the linkages. So how do the arms move in order to do a certain task? And we've got Nav2, which is high-level mobile robot navigation. So something that's got wheels and it's moving around. PyBullet, we've got physics simulation. So as part of simulating your environment, so PyBullet handles the physics. GIM is a package for reinforcement learning. TF2 is for robot transformation. So as you're dealing with all these arms, and there's a whole lot of different coordinate systems, and the TF2 package keeps track of all the orientation and the position of all these coordinate systems. There's also a package for control loops, and then we've got our core libraries. So there's over 800 total packages in ROS. So lots of packages in some of these more complicated applications. Here, Nav2, we showed the video in the beginning. SLAM is simultaneous localization and mapping. So there's a lot of different modalities that a robot can use to sense the world. And so the idea is you're kind of building a map from your sensors, but you're also navigating through that and estimating your position based on the sensors. So we've got 2D LiDAR, which is scanning and seeing where the walls are. We've got stereo vision. So stereo vision, you've got two cameras and you detect a point in each of your cameras. That's the same point. And based on how far different that is, you can tell the depth. That's really good for outdoor environments because there's lots of texture in your environments, and it's really easy to say what's one point in one camera and one point in the other camera. If you use that in an indoor environment, you might have freshly painted walls, which are just a flat color, and it's hard for your algorithms to see what's the exact same point in one camera versus the other camera. For indoor environments, these RGBD cameras are really useful. So the idea, there's a channel that you don't see that's projecting light against the wall, and that channel that's projecting the light is sensed by the camera and able to determine depth from that additional information. But it really only works in indoor environments because you've got to project that infrared light. There's also monocular vision. So if the idea is you just got a single camera that you want to navigate, there's a lot less reliability. There's a great paper they've got on the Nav2 website that is it's a research paper that talks about lots of the different types of navigation and a lot of the pluses and minuses. And it was released about a year ago. So it's got the current up-to-date research on a lot of these different types of navigation. But you can you can do monocular vision, but it's less reliable. So you've got to be able to kind of infer distances from monocular and see how things move over time. So it's more prone to error, but it can still work in some environments. One of the neat things that I found in navigation 2 is behavior trees. So it's essentially a state machine generalization. And so we can think of, a state machine as different states that a controller passes through. But as you add more sophistication to robots, it becomes, there becomes a limit where you have so many states in order to do some complex applications. So they've developed this behavior tree concept, which is essentially composing different state machines together into this high level structure. And I've done so many different state machines. I was like, oh, this is something pretty cool and pretty new, different way of thinking about it. Okay, so this is nav 2. Move it. So we've got the motion planning. So we've got to deal with inverse kinematics. So if we want our end effector to move on a certain path, we've got to think about what are all the mathematics of what's the angle of each point in our robotic assembly that's going to move from point A to point B. We also might have collisions. So this robotic arm might have to avoid things. And there might be some task where it has to pick up things. So we've got to think about hand-eye coordination. So we've got a view in our camera, and then we need to do the coordinate transformations of when I see something move in the camera, how is the robot moving? So we've got to think about all these kind of 3D geometry of how do I translate something in a camera to a physical motion. This is used in a lot of the pick and place applications. So a lot of the companies that you work with, Amazon itself, have all these robots to do pick and place. And so there's a lot of robots that are kind of doing a lot of this factory work, doing a lot of stuff behind the scenes, and making people more productive. I don't say taking people's jobs, just making people more productive. And so lots of interesting stuff with this application. Jim, I've got another neat video here. So reinforcement, what is reinforcement? So the idea of reinforcement is you're having an agent that's acting in the environment and getting a reward. And this action is following a policy. And so you've got a mathematical representation of the policy that the agent is conducting. And as you are successful or unsuccessful in the certain task, you get rewarded or punished. And as you get rewarded, the policy gets updated through some optimization rules such that you come up with a policy that does the task. So you're kind of building up and this happens through lots of iterations of experiments as your simulated environment is kind of running through all these different cases. You get rewarded for when it works, and eventually you come up with a policy that's able to do a particular task. And so this has been in a lot of the university research for a number of years, and it has matured through the years. And we've got all kinds of machine learning frameworks that is really pushing the boundaries of this. So there's a lot of really neat stuff in this area. Let's see. Okay, I'm gonna give a little demo here. Unfortunately, I don't have a live robotic demo, but we're gonna do a simulation. Okay, so we've got, over here on the left is Gazebo. So this is our simulated world. So here we go. We got a little robot here, and he's got sensors looking at the different marks in the system. On the right, we've got its internal map. And so this is showing the internal map that is the robot's generated for it to navigate by. And so it's got a position estimate, and it's seeing the local area of the environment. And we can tell it to go to a different goal. So we're going to say, here, go over to this area. And so it's generating a path that can move to that other area. It's starting to move through that path. And as we see it moving, it sees different sensors in its local environment. All right, now it's reached its goal. We're going to replan it and have it go somewhere else. All right, so there we are. I put some references in here. There's some great tutorials on the ROS documentation. Galactic is the latest one, pretty similar to Foxy. We've got there's some great websites for the navigation for the Nav2 and Move It To. So whenever there's a package with a 2 on the end of it, that's just emphasizing that this is a package for ROS2. So Move It was ROS1, Move It to ROS2. And put some links to RoboStack as well. Recently, there were some talks released from ROS World 2021. So the recordings just recently became available. So this link is to the kind of latest, greatest information about ROS. Questions?
Yeah, I do have one kind of related to our conversation earlier. So like when you have the pub sub type of communication, can you have those communications going over the network, like to a different machine, or is it just internal on the same machine?
Oh, absolutely. And that's what kind of enables a lot of this cloud computing with robotics. And so like you were saying before, you could have a robot that's that has sensors on board, and then it's publishing those sensors to some kind of cloud computing cluster. And then you can do the heavy lifting on that compute cluster where it's, running the reinforcement learning, or maybe it's doing a TensorFlow application on your video data, anything like that.
It's cool. So people that are still using Kinect, I know when I was playing with ROS, all the talk was about Kinect. They're still like using the actual Kinect sensors, or there's other options out there.
Yeah, there's a whole class of that RGBD camera now. So there's a bunch of vendors doing that now. It used to be just Kinect, but now there's a whole plethora of vendors that have those RGBD cameras.
Cool.
You mentioned building robots with your daughter. Were you going to talk more about that?
Oh, right. Yeah, I've got a son and a daughter. We've got this, let me see if I can show it up here. Ooh, I got a picture on it. It's a little bit blurry. Let's see if I can make it. Here, I'll show you this guy. Yeah, so my son is 7 and my daughter's 5. And so we bought this Mbot robot. It's fairly reasonable. It was $120, I think, to put it together. But one of the things that's really neat is there's many ways to use it. So out of the box, it's got this tablet app and it's got a joystick. And so this is something we can, put it together and my kids can instantly be entertained by it, drive it around. They've also got some built-in applications. And so you've got the sheet with a figure 8 and it can follow around the figure 8, do some obstacle avoidance. But then they've also got some simplistic coding. So they've got this Blockly, which is kind of a Scratch derivative. And so my son's put together little programs with that Blockly Scratch to do different actions. But is this a robot for my kids or is this a robot for me? So I like to have fun too. So there's also Python libraries that can connect to the controller, and you can kind of do simple Python scripts and applications that do different things. This one I supplemented with a Raspberry Pi 4, and so it's got the Pi controller that runs the motors, but then it's supplemented with a Raspberry Pi. So on that Raspberry Pi, we can run a lot of different things. And with the Raspberry Pi 4, it's got a 64-bit, it's the ARM8 processor, which means you can install the ARM64 Ubuntu installation. So there's actually more capability you can get if you do Ubuntu with ARM64 than you get with the standard Raspberry Pi OS, which is 32-bit. Also got a camera on here, and so this is kind of what I eventually want to get working with ROS, but I'm still a little bit learning, so not quite there yet. But what I like about this is there's so many entry places in there. So it's kind of basic for the kids, then they can learn more, or we can do something really sophisticated and do, you know, navigation and machine learning and all that kind of fun stuff. But this probably, you know, good segue into the next talk where we're going to talk about learning things.
Any more questions for Greg before I take over here?
Yeah, hi, my name is Ed Dawson. I had a question just about the hardware in the simulator. Does it know about a lot of hardware? Do you know what I mean? Like, does it give you like a notional robot car with DC motors or something, or do you have to specify exactly what you're planning to use?
Yeah, you got to specify what you're going to use. You got to kind of configure all those pieces of hardware. There's these launch files. You can specify lots of different parameters of how you want to configure, and so there's lots of different ways you can configure the respective hardware that you've got connected.
Awesome, thanks.
I have two questions. First of all, how does a 5-year-old or 7-year-old cope with Python? Well, what's the reaction? Tell us.
Oh, well, they don't actually have to use Python. It's just an app. And so so it's an app they can kind of click, and so there's a little joystick, they can drive it around. And Blockly is not really Python, but I've seen a few applications where you can build a program. So Scratch, Blockly, it's kind of a visual programming. So you've got blocks that represent functions. And so one function might be move. One might be turn a light red. And so you can kind of drag and drop these blocks together to come up with programs. Some different versions of Blockly Scratch have the ability to do this drag and drop visual programming, and then click a button and see what's the corresponding Python program associated with that.
The second question I have is, you mentioned that Conda, like it uses Conda rather than virtual end, which makes sense because Conda can do PyNoise. But can you talk a little bit more about what's happening there and what works and what doesn't work?
Oh, right. Okay. Yeah. So there's the standard way of installing ROS is through apt. I should have put a slide together about this. So if you want distribution packages, you'll use like an apt get install, and that'll pull in the ROS packages for a particular distribution. And then there's a bash script which kind of enables your environment. You can also build ROS from source, so you can get the source to respective packages and you can build those packages. But there's a group doing RoboStack, which is trying to convert this ROS build structure into the Conda infrastructure. But it's only a few people working on this. I was looking at the link here. Let's see. Oh, and I've noticed I'm one of the 4 contributors, so I just have a very tiny amount of contribution to this package. But Tobias and Wolf are trying to drive this effort to make this Conda installable, and so you don't have to go through apt-get and have sudo permissions. You saw that I was running this in a virtual machine, so it was much easier for me to put it in a virtual machine because of the complexity of installing ROS and having it kind of be installed system-wide versus isolated into a package. So there's still a lot of work here to make this to make this RoboStack work. But Tobias and Wolf have been putting a whole lot of effort into making this ecosystem a little functional and working. So
thank you. Lauren, did we lose him?
I'm here, yeah. Any more questions?
I saw that Sherry had her hand up a minute ago. Sherry, was there a question that you wanted to ask?
Sherry usually writes her questions in the chat.
You know what, you're right.
She says,
But
what's the
check
name of
out
the
that she's
scratch
not just
derivative?
documenting.
Yeah. So I think somebody else already said it, but there is from Sherry a little bit ago a question. What is the name of the scratch derivative that you're using here?
it's Blockly.
Blockly.
It's a commercial company, MakeBlock, that makes some of these education robots, and their derivative of Scratch is called Blockly.
Awesome. Thank you so much for that.
Yeah, and if you have kids and then you're buying one of these robots that have Blockly, and also they can be remote controlled, make sure that you buy a robot that cannot be remote controlled. Because I bought one of those robots a while ago, and the kids figured out, okay, I can remote control it, and then they never program it. So it's a lot easier to go and have fun remote controlling it, but than programming it to do things. But yeah, so keep an eye on that. Make sure you cannot remote control it. It's just like make sure that you can only program it.
Well, there's different strategies. So my kids are only 5 and 7, so having them program is but that once it kind of sparks that interest and intrigue, I found that sometimes they want to do more. Like my son started just playing around, but then he wanted to do Blockly, and now that he's doing Blockly, he says, I want to do what you do, Daddy. I want to do Python. So
nice.
So it sparked that interest, even though it's just kind of basic driving it around.
Yeah, that's neat. Cool. Are there any more questions?
I was trying to see if there's a behavior-driven development for learning for eye-hand coordination. That's what I was looking at for an app. As far as an educational AI interface, human interface for education.
For education, let's see. MoveIt has the eye-hand for the robotic manipulation. The Gym is really neat for reinforcement learning. Gym doesn't have to be used with ROS, or Gym can be used by itself for reinforcement learning. As far as human interface, I'm not sure. There's a whole lot of stuff out there, but I'm not an expert on that.
Thank you. That was so great. That's awesome.
Thank you.
Well, I guess there are any more questions? Going once, going twice. All right. Well, thank you. Thank you, Greg. This is awesome.
Thanks, everyone. I'm excited to talk
Yeah, you got me excited again about ROS. I'm going to go and dig all my Raspberry Pis. Cool. All right. Thank you.